All right, so at this point, we know enough now to build our own nuclear bomb, right? Which is obviously the whole point of taking this class is to learn how to do that. So let's real quick we can go through that and kind of talk about how this works. This is going to be just an exercise in balancing nuclear reactions and kind of seeing how this works. So when you have uranium 235, so how to make atomic bomb. When you have uranium 235, uranium has an atomic number of 92. So we have 92 protons and whatever this is, 143 neutrons. Okay? And that uranium is hit square in the nucleus by a neutron. Okay? What's going to happen is that neutron is going to be absorbed, and we get uranium 236. Right? Notice that we're balancing this equation, right? 235 plus 1 for the mass on the reactant side is 236, and 92 plus 0 is 92. So we've balanced our nuclear equation. This is a nuclear fusion reaction. Uranium plus a neutron equals uranium 236. Now, uranium 236 is incredibly unstable. So first we undergo fusion here. And the way that this is done, I mean, if you're actually building an atomic bomb, this is the hard part, getting the neutron to stick to the uranium, right? And so the way that they did this was kind of twofold. One, they find that if you do this reaction in water, the neutrons just move too fast and they never hit the uranium. And so what they needed was a way to kind of slow that down. They figured out that if you use water that has hydrogen 2 instead of hydrogen 1 instead of H2O, you have deuterium oxide, D2O. Deuterium is just hydrogen 2. So if you use a slightly different isotope of hydrogen, you can slow down those neutrons and then they'll hit the uranium and they'll stick. And so the way that they did this is they set up a uranium in hydrogen 2 water, deuterium water, heavy water, they called it, right? And then outside of that, they put a bunch of explosives and then just conventional like dynamite kind of explosives. And those explosives, boom, kind of drive all these neutrons in toward the uranium nucleus through the heavy water. And so then those neutrons hit the uranium 235 nucleus, they become uranium 236, which releases a fair amount of energy, right? Fusion reactions in general do that. But that's not even the bad thing, right? The bad thing happens once uranium 236 falls apart. And so this is going to undergo fission, where we go from combining nuclei to now having it break apart. And so nuclear fission is going to result in krypton 88 plus barium 145. And of course, they figured this out by observing what the results of decomposing uranium 236 are. And so you get these two things. Now notice that we have balanced the charge. We have 36 and 56 adding up to 92. But we haven't balanced the mass, 88 plus 145. And so that only adds up to 233, right? So we're 3 mass units short. And so what this produces is it produces 3 neutrons. And of course, these neutrons are fired back into, every time this uranium 236 falls apart, it creates more neutrons. Those neutrons hit either uranium 235 and they stick to the uranium 235 and make 236, and it keeps going, but every time you're producing more and more neutrons, and every time you produce those neutrons, they undergo more nuclear fusion, right? And every time we do nuclear fusion, we lose a little bit of mass, and that mass is converted to energy at a huge conversion rate, right? Because times c squared. It keeps going and going and going, and you get this huge outpouring of energy. That is an atomic bomb. Right? The reason that these are such hugely destructive things is because they produce so much energy, and they kind of just keep going until all the uranium is used up. So if you want to do this, well, don't, because why would you? But if you want to do this, these are the things that you have to have this kind of self-sustaining reaction where the uranium hits the 235, or the uranium 235 is hit by the neutron, and that reaction produces more neutrons. We get this chain reaction where more neutrons you produce, the more fusion reactions take place, the more energy you produce. And of course, it just kind of runs away from you. So of course, then the question was, we don't want this reaction to run away from us all the time. Can we harness that energy? Can we actually control this reaction and not have it just become a huge mushroom cloud, right? Because we are also producing huge amounts of energy here every time we do this reaction. So we should probably put that in here somewhere, plus energy, right? And so in nuclear reactors, we use kind of the same idea, except the problem is we have too many neutrons flying around. And so in nuclear reactors, what we do is we add boron 10. Right? And so boron is element 5. It has obviously a mass of 10. And what happens with boron 10 is when boron 10 encounters a nucleus, you get this kind of hybrid of fusion and fission. These two things stick together, but then the boron falls apart again. And what you get is helium-4 and lithium-7, both of which are nice, stable nuclei, right? But notice what it doesn't produce is plus no neutrons. And so if you've ever seen a nuclear reactor, you know they have these, what they call cooling rods, right? And so these cooling rods, they sit in this big swimming pool where in the reactor, right? And the swimming pool is, of course, you know, the medium where the neutrons are flying through the water that's in there. And what the neutrons do is when they hit the boron, these cooling rods are made of boron 10. When the neutrons hit this boron, they are converted into helium and lithium. And what that means is that they hit the boron instead of hitting the uranium. And so this fusion-fission cycle is a little bit less energetic when you add the boron 10 because not all the neutrons get cycled back into reacting with uranium and producing the fusion energy and the mushroom clouds and all that other kind of stuff. So this is why nuclear reactors actually work, even on the same principle that atomic bombs work, because what we found is we found another balanced nuclear reaction that allows us to kind of soak up these extra neutrons, right? So if you have a lot of boron around, we can soak up all these neutrons and prevent this chain reaction from running away from us and getting out of hand. So a practical video lecture, how to make your own atomic bomb or how to make a nuclear reactor and not make an atomic bomb. You can kind of choose for yourself which one of those you find more useful.